course, I've just started recording. I am going to do a quick recap. So thank you everyone for joining. The reason for me starting this was I wanted to liven the London Reinforcement Learning meetup up and see if we can get some meetups going and some discussions going. So that's my motivation. The purpose of this is the terminology and the key concepts in reinforcement learning, almost as though you didn't know anything about it, or you've heard about it, but you don't really know anything. And I just want to run through all the key pieces of terminology and concepts, and then actually start to discuss some of the complications, we might get that far, in how it is used in the large language models. But I'm going to go back to the first slide and give a quick recap. So this is welcome to this meeting. We're going to talk about terminology and concepts. The idea behind this is just talking about terminology and concepts is the fact, a book by Josh Kaufman, I hope I'm saying that correctly, To Learn Anything Fast, a Good Scaffold is Needed. He's written a book on this. The first two chapters are available free on the internet. Read them. They're really, it convinced me that getting the terminology correct and the concepts in my head is the fastest way to learn a new topic. Then it's far easier to bolt new concepts and information in. Point one, what is reinforcement learning? Reinforcement learning is about what action or move is to be taken next. Do we wish to, in this situation here, in a game of chess, what should white do? Driverless car, do we brake, do we swerve? So some of the terminology, state. Reinforcement learning, classic reinforcement learning has been built up from state to state transitions. Everything that the agent needs in order to make a decision must be included in the state, or the agent cannot be optimal. So in this case, the white pawn has moved forward one. It's a different state in chess. Terminology, episode. You have a series of state transitions, and then at the end of the game, this whole series of states is called an episode. Then the episode ends, then you start another episode. Some things do not have a natural episode, such as weather. Then you have to force one onto it. In this game here, we're at the end of the game. The white has just won because it's put the black king in checkmate, and we assign it a reward of 1. Now, this is terminology that I got confused often, and this is the difference between reward and return. Reward is a reward that you get each time you move, each state change. The return is the sum of all the rewards for an entire episode or game. This is very important because you can influence an agent to play a quick game or to do something more quickly if you set this up one way but not of the other. So we have lots of states. So this is different places in the board game. So we have, in this case, this is a small set, state E, state A. State E, there's a 30% probability to move back to state E. A, there's a 70% probability to move to state A. Now, if this depends on the current state and only the current state and action, then this is called a Markov decision process. And so then we can, some mathematical properties hold on this, and then we can start to bring a lot of maths to bear on this, and it turns out to be very useful. Okay, so next slide. So now we're starting to get into the meat of reinforcement learning. We have states, we have episodes, we have actions, but the probabilities, calculating the probability of moving from E to A, when we do something, how do we actually calculate that? This is the core problem of reinforcement learning. Okay, so state-based reinforcement learning. So we want to learn what action is needed to transition from our current state to another state, and we want that state to have more value, to be more valuable, to be better. So what we do is another piece of terminology: policy. We store all this information in what is termed as the policy, and this is what is learned while you are while you're proceeding through reinforcement learning. Yes. More. Okay. So this is just a very quick summary. State value function. So this is a function that will give us the expected reward of this state. So any particular state that we're in. Action value function. What is the total expected reward of a particular action in this state? And policy. Given a state, what is the best action and its expected reward? And there's often the policy is often abbreviated as pi, the action as q, and the state value function is. So this is a sorry, excuse me, I'm just admitting people who are joining. So note that terminology, the notation tends to be consistent, well, somewhat consistent, which is useful. So now that we've talked about states, actions in these functions, how is this solved, and how did the field come to be? And this is more terminology. So this is the comes back to the Bellman equation, and it based on a certain type of modeling. That was, you can model each one of these states as a one-armed bandit, which is it's some process that we don't know quite what it is, but it has some probability of going to state A or state B. How do we learn those probabilities? That problem is called a one-armed bandit. When you have multiple of them, it's referred to as a multiple-armed bandit. The Bellman equation tells us how we can start to translate between the state value function, action value function, and the policy with that model in mind. So it's very useful. I'm not going to go into the detail here. It is a core concept in reinforcement learning. I'm going to go now on to terminology. No, I'm going to pause and just ask: are there any questions? Yeah. Julian, yes, please.
Reversing back to slide 8, if you don't mind, is it just a coincidence that those pairs of probabilities add up to 1?
No, because they're probabilities, they must add up to 1.
Right. So right, because I was just thinking they look like weights, but weights could be anything, or biases. So these are probabilities, and I get it; they have to add up to 1.
Great, but this is a good question. I haven't talked about neural networks yet, and I may not really talk about neural networks. So this is not neural networks. So, but excellent question. Thank you.
Grant, thanks.
Any other questions? No. Okay. So it functions. Okay. So terminology. So this is some algorithms that are going on. So some of the key algorithms that you will see, and so this is if you're learning reinforcement learning for the first time, are exhaustive search, Monte Carlo, temporal difference learning, and dynamic programming. And I'm just going to give a couple of bullet points on each. So on exhaustive search, essentially what you do is you start your game or your driverless car, and you through every possible combination of every action in every situation that you can, which of course for chess is because we have computers that we can play against. This is easy. For a driverless car, when you break it, crash into something in 3 minutes time, and then you need a new car, it's going to get very expensive. So that's one problem. You need a environment that you can simulate the environment in, otherwise the cost gets prohibitive. But also for exhaustive search, the number of states explodes, as well as the number of actions. So chess, it's huge. Think about all the different combinations of how you could place the chess pieces on the board. Each one of those is a new state. And in fact, it's 2 new states because either side could have the next turn, which must be included in the state. Monte Carlo. So what Monte Carlo does is you start your game of chess. You're playing against a chess computer, say. So what we do is we start taking actions at random. We don't know how to play chess. We try and move the king to begin with. It can't, it's blocked. So nothing happens. So I go back to the same state. So then I try moving a pawn, and then it goes, oh, okay, that worked. But now we have the problem of the allocation of the reward, because this isn't worth any points until we win or lose the game. So what we have to do is then keep rolling the dice, keep selecting moves, and seeing how long it takes to finish the game, whether we get a reward or not, and then we start allocating that reward back through the policy to all the states that I moved through in order to win the game. So the problem with this is it doesn't guarantee, mathematically, it doesn't guarantee convergence unless I play an infinite number of games, which is quite a lot, and it's very sample inefficient. You can wander around in parts of the space, like so in a chess game, that no 2 humans would ever play because it's just silly. But this is how it's done. It's done randomly and just moving right through the episodes randomly, and then backing up the reward to store on each state. Temporal difference learning was a slightly better. And so what this does is, rather than picking an action at random, well, that's not quite true. What you do is you have a policy that you're learning, and it will suggest move a particular pawn. So you move that particular pawn. If it's the best move, that's what you do. Apart from with some probability, say 5% or 10%, you just take a random action in this state. And so this is quite good, because as soon as your policy starts to learn, you will tend to concentrate through the area of the state space that works. So this was good. The person who found this algorithm essentially solved backgammon with it quite some time ago. I think it was in the late 80s or early 90s. And then it wasn't quite understood how well that worked until a little bit later, and people refound his PhD thesis. And the next piece of algorithm terminology is dynamic programming. So this is a way of breaking down any problem into a series of smaller sub-problems. So the classic one of doing this is factorial. No, sorry, that isn't the classic one of doing this. What is it? Not sure what a good example of what dynamic program is usually used for. But essentially what you do is you break a large problem like a game of chess down into lots of smaller problems. And then you start propagating again the reward back from the end of the game back to the beginning. It actually turns out that the best way to do this is from the end of the game and back. And so this is how it's often done. I know an example for this, and that is if you're trying to find the shortest route from here to, say, Edinburgh, and you know the distances between towns, you can start working through to find the shortest path. And they essentially the algorithm works from the end, because you know you're going to get to Edinburgh. If I go in some random direction from London, I may not get there. Any questions? You're all good. Terminology, concepts continued. Okay, so now we have on policy and off policy. Again, you'll see this in the literature. On policy, off policy, model-free, model-based, and continuous and discrete. So on policy, off policy. So in the example where I did TD learning, where I have a policy that I'm learning, and I select the best action from that policy, and if it's initialized, they'll all be set the same, so I just essentially take one randomly. Otherwise, so take one randomly and move until I start getting some signal and start training, and then I'll take that one unless there's a small chance I take another one. Because the policy that I am learning and updating is the same policy as the one I am using to take actions and select actions, then this is called on policy. Off policy would be something kind of like Monte Carlo, because the policy being used is essentially the roll of a dice. It's random. We're not using the policy that we're learning in order to select the next action. And there are some algorithms that have taken this even further, and the way of generating paths through the games and then what we learn from are totally decoupled, so that they are called off policy. Then also we have model-free and model-based. All the terminology and the concepts that I've given you so far can be applied to model-free reinforcement learning. Model-based reinforcement learning is if somewhere in memory or on disk, you have an actual model of the agent is building a model of the world and how it works. The advantage with this is that the agent can call on that model to say, give me the next, if I move my pawn and then I do this and this and this and this after it, what happens to its internal model? And it can update this internal model as it goes. That's called model-based reinforcement learning. I'm going to do a talk on that on a new paper that is not that new paper, that is using model-based reinforcement learning in 2 weeks. So if you'd like to, please come along to that. And the third concept is continuous and discrete. The 2 examples I gave at the beginning of the talk was a chess game. These are discrete moves. I move the pawn or I don't move the pawn, and I move it 1 square or at the beginning 2 squares, and that's it. I can't do anything else. In the driverless car situation, you can turn a little bit, you can turn a lot, you can brake, you can accelerate a little or a lot. So they are continuous situations. Yeah. Okay, and then a summary of the algorithm space. So in reinforcement learning, there are the 3 major dimensions in which algorithms can change, and there are more, but these are the ones that I've started to talk about. And so essentially We have temporal difference learning, which is like the update width is this dimension. So I'm only trying to take one action each time and update just on that one action. If I did dynamic programming, I can be doing multiple actions at the same time, essentially getting the reward for all of them and updating them all in one step. And then there's update depth. For Monte Carlo, I can roll my dice lots and play the game of chess out. And so I've got an entire game of chess here. And then what I can do then is I can then start learning from that entire game of chess. In fact, I can't really do anything until I've got the entire game. And then in this dimension, I placed on policy and off policy. So here we're using different temporal difference learning is using the same policy as it's updating to draw or generate the next move. Whereas something like Q learning, if you look it up, it doesn't do that. It uses an off policy uses two different policies, one that it's updating and the one that's used to generate the data of the move. Sorry, generate moves to take. Yeah. Any questions? No. Okay, and now this one is a beast of a slide. And I've possibly gone a little bit fast, but that's fine. Admit someone's wanting to join the call. Okay, so we've gone through state, we've gone through values, value functions, we've gone through the different dimensions on policy, off policy, model-based, model-free. So one of the most robust algorithms at the moment, or that is used mostly in industry and in literature to benchmark against, is proximal policy optimization. And so now what I'm doing is I'm stepping another level of abstraction away, massively another level of abstraction away. And I just want to show how the way that reinforcement learning is talked about in the literature for learning it is generally, as I've said it up till the last slide. This now is how it's being used in terms of a large language model, which when I first heard about it, I did not feel that it was true reinforcement learning, and now I think I start to understand how and why. So in the terms of playing chess, we're trying to get, the actor is trying to learn a policy that allows it to pick what is the next move. In the large language model case, we're getting a situation where the actor is wanting to influence the large language model to produce the next token. What token should be next? What should be generated? So it's at that level that the large language models are using reinforcement learning. Kind of. There's more to it than this, really. So in this particular model, what's happening is you're getting input, which is the user input, asking a question. You've got a large language model here that generates output. We then have a value model. So this is the value model function, or value function that we mentioned before. Essentially is being taught here. This is another large language model. The reward model is frozen. It's not being updated. We assume that we've got this and we've got the reference model. The reward model is saying how was trained on lots of human data, human preference data. So do I prefer this answer or this answer better? And humans will pick one or the other. This model then started to learn which one was predicted which one was preferred by humans. They were not wandering off into the wrong language. They were not answering with maths for a simple question. And then the reference model is is essentially the initial version of the fine-tuned large language model before we start this reinforcement learning on it. So that's just a frozen version of that. This KL here refers to a KL divergence, and I'll mispronounce the name if I actually say it. And so what this is doing is it's making sure that if these two vary too far in their distributions of the tokens that they produce, so if something starts going off into Chinese or something like that, when it's an English question, this will be penalized, and the reward will be reduced. Yes, and then here we have a situation where I haven't gone into the detail here, and I don't think I wasn't going to, on the basis that this is not, this would need to be an introductory talk, and so this essentially is going down to an advantage of which one of the outputs is preferred and used back in the policy model, and then the policy model is updated by a small amount. This is an example of an off-policy model because there are two models here. One is the actor, the one that we're learning, and the other one is a critic. So this one is saying whether the value that was produced is good or bad. So this is referred to as an off-policy reinforcement learning. Yes. Any questions? No. Yep. Moving on. This is another one that has been talked about in the literature very recently. So this is a different way of setting up the large language models and what is being trained and updated. And if you notice, the difference between the two is this one has two models that we're learning, whereas this one only has one. So this method is far better on memory consumption, far better on compute, and it has a lot of the same components as this. And one of the recent LLMs that came out has this. So that's why I've included that here, just to say that it's at this level of abstraction that the changes are occurring at the moment. So look out for these. And if you just look at this and you're beginning in reinforcement learning, I think it would be a bit confusing. You would sort of need the other concepts first. And really, that's all I really wanted to talk about. I just wanted to say my key sources for this talk was this book here. The full PDF is available online. There's code, there's other things. More sources. There are University College London has lectures online, so does Stanford, and you can go into more detail and in particular algorithms as well very easily online. So thank you. Are there any questions? Yes, Julian.
Can you make the slides available, please?
I will absolutely make the slides available, and I'll give you a link, and I'll email that out to everyone who RSVP'd on the meetup group, and I will put the recording online. And what else will I do? Oh, and also the next talk is more detailed. It's going to be on a particular paper, and so that's on the screen at the moment. So it's Thursday, the 3rd of April. It's in conjunction with the InPlan paper group, meetup group. And so we're going to read through a paper that was part of someone's PhD thesis, where they started to get model-based reinforcement learning actually working on games, which is the first one I saw, and I find that's quite interesting. Yeah. Anyone else? Any other questions?
Could you could you just say in a sentence or two, give me anyway, more of an idea how the terminology you've gone through will how would that play out in the simplest kind of example? I know it's probably for 6 lectures down the line, but it's just it helps me if the terms then are put into some kind of practical example, if you can think of one off the top of your head.
I can. The practical examples that I go back to is chess and then large language models, because I think they're the kind of the two that people sort of think about most, or probably are kind of familiar with. So with chess, it's closed, it's understood, it's a finite environment. You don't get any reward right till you get to the last move, which is annoying, but they found ways around that algorithmically.
Could I just what about when you get pieces taken? Isn't that a kind of negative reward?
No.
Or no,
So
it's not.
No, hang on. It depends on how you set it up. And so this is the key thing with reinforcement learning. So this is a really key thing with reinforcement learning. It depends on how you set up the rewards as to what you're encouraging your agent to do. And there is a term called reward hacking. And so this is where people set up the rewards like negative reward for having your piece taken, positive reward for taking someone else's piece. And then all of a sudden the agent does very weird things. It's running away from the opponents. It's really strange stuff that you don't want it to do. So
this is a bit like the paperclip thing, where you have an LLM that's only designed to produce paperclips, and it wipes the world out in its desire to produce paperclips.
It's exactly that same problem, and it's easy to think that it's easily solvable by adding more reward and tweaking this.
I get it.
And there tends to be another consequence that you didn't think about.
Yeah.
And so that's one part of the question. The other part of the question, as I understood it, was where is this going to go with in the future with models? And I think what they've done is they've shown that reinforcement learning can play chess. It can play Go. Go is the state space in Go is astronomical. And they've shown that they can do this. Now, for large language models, the next move essentially is one of about 70,000. It's the next token that you can generate, and a couple of tokens makes a word. So, what is the next token that you generate? And in this model, in this diagram here, what people have managed to do is they have managed to essentially get set it up in such a way that I don't need a real car to drive around the streets. I don't even need an environment to an opponent chess player to play it against. What I can do is I can start to train a large language model to give better and better answers based on on a reward model, which is people's preferences. So this is going to get better and better, but I think it's going to hit an asymptote, and the reason for that is because it's what is the reason for that? The way how would I describe in this case, the reward model that people have given here might be. So I'm going to come up with a silly example. If we've done the first 5 school years of maths, and we've got those kind of questions, and we've asked people to give their preference of answers in that space. Now, so we've got those answers, we've trained a model on that data, and now we have a reward model. The Now we start going later years of maths, we start asking these kinds of problems. It will get better at those, but only to a level, because it won't do, it might do a year or 2, 3 years, 5 years, more complicated maths and be able to build on it. But truly innovative ideas, it can't really do. It hasn't seen enough in this reward model to be able to go that far. Does that answer your question?
Yeah, no, it's helpful.
Yeah.
It's helpful.
So then at that situation, you'd need to get more human preference data done. You'd need to understand what the large language model gave you. You'd need to check it, that it is correct. Some of it, curate the data set, say what is better, and then start retraining again. And the disadvantage with this is, at the moment, is that it is getting more and more expensive.
It sounds human intensive.
Yes. It's hidden, but yes. I mean, there are 30,000. There's estimated that there's 30,000 people employed full-time at the moment, just saying which LLM answer they prefer.
Gosh. Yeah.
Which I mean, that's great, but that tells you on this curriculum, right? On year 10 maths. Okay, fine. But what happens year 11 or year 15? You need to keep doing this.
Yeah, interesting.
Any other questions?
I do have one more, which is a kind of far out.
It's a discussion. I find a discussion far better, and I think people join Meetup because they want a little bit of to learn and to meet people. So yeah.
Just one other thing. Are these presentations going to lead to helping us understand better what something like R1 has done, which I think reinforcement learning was a huge part of R1?
Yes, I wasn't going to go into the large language models because they don't intrigue me much. I think we're going to start hitting the limit on those, and I think reinforcement learning is more interesting. So my focus is on reinforcement learning. Certainly, if you go, so R1 used PPO from memory. It used
okay,
right.
Okay.
R1 used this method of training, and so there's another step involved before, because they trained a model with human preference data, and they tried to get that better, and then they started generating data from that with that model, and then with that one, then they started using this PPO to further train it. So that's off the top of my head. I'll probably be wrong on part of that, but broadly, I think PPO is what they used, or the next one, RPO. But yes.
Great, thanks.
Any other questions? I had a question. Great. So if I work out how to see the question more. So as the reinforcement learning group, would you be following more meetups, touching topics more in depth? Yes, absolutely. So yeah, absolutely want to go into more depth. So the next paper is a paper by someone, and it is on a way that they used model-based reinforcement learning to get human level state-of-the-art results on Atari games. So yeah, a lot more depth. Okay, cool. And so yep, it's So I mean, it was meant to be a and it says I can just share this. Julian, editor, allow anyone. Yep. So I've just shared the presentation in.
Right.
In the.
Thank you.
Messaging.
Right. Terrific.
And anything else? So ping me on the via the meetup group if you'd like. And also if you'd like anything in particular talked about, let me know. And if you'd like to meet up and how you would like to meet up in person, also let me know.
That would be great. There, as I've discussed with you privately, I don't think there are enough in-person meetups.
Agree.
Around AI at all, not anywhere near.
Absolutely. Yeah, I agree with that. Totally. So if there are no more questions, I'll end it there, and hopefully we'll see everyone next time.
Thank you very much, Dwayne. That was great.
Thank you very much.
Very welcome. Cheers, guys.